Good afternoon, everyone. I'm Calvin Joseph, and today I'll conduct your Week 7 problem solving and doubt clearing session of the NPTEL course, Digital Electronic Circuits. This was taught by Professor Gautam Sahar, and I am a PhD scholar at IIT Kharagpur. So today we'll be considering Week 7, where Sir taught regarding various, give the introduction of sequential circuits, where Sir has discussed about various flip-flops and D flip-flop, SR flip-flop, JK flip-flop, what is edge triggered, what is level triggered, how do you find their characteristic equation, their excitation table, and state transition diagram? And how do you assess, how do you analyze these circuits? All these things we'll be discussing. We'll be considering various sums and which will be helpful and useful for you to solve the assignment questions for this upcoming week, week 7. Okay, so let me share my screen. So today is week 7 and we'll be discussing mainly about sequential circuits. Okay, so till now, what we were discussing mainly, we were restricted to combinational circuits. Okay, where there's no concept of history. There's no concept of storage / history. So that's why they have come up with what are known as, bistable circuits, which can store data. These are for storing data. They can store 1 bit, 2 bit, n number of bits, etc. These are storage circuits, like digital storage, like which is really increasing in popularity these days, mass storage and everything. Okay, so for that, one basic circuit is considered. That is known as a latch. And we will start with the basic SR latch. Okay. So that has this diagram. You use 2 NOR gates for this. The NOR gate, another NOR gate. Here, this is your input R. This is your input S. Your output is renamed as Q, and this is renamed Q bar, as you will know that they are complementary to each other. Now, in addition to having inputs and output, what we have here is feedback of the output. That is, the output over here is fed back as an input to this. And this output over here is fed back as an input to this. Okay. And because of this concept of feedback, it will sort of like latch. It will hold on to that data. It can, store. There's a concept of storage because of this feedback. Okay. So let's see. So this is the simple circuit for an SR latch, where if you say, we'll consider the truth table. Okay, let me write the truth table. Here S, R, Qn, that is your initial, and your Qn plus 1, that is the next state. So S is 0 and R is 0. Qn plus 1 will be equal to Qn. Okay, anything. Now if S is 0 and R is 1, then Qn can be anything, but Qn plus 1 will become 0. If S is 1, R is 0, then Qn plus 1 has to be 1. And if S is 1 and R is 1, these are actually, forbidden inputs. They are not accepted. Okay, they are not allowed. Okay, so we will look into a certain simulation of this to get a better idea of it. So, opening the SR latch. Okay. So this is a NOR gate. This is a NOR gate which is present. Two NOR gates are there. This is your reset. This is your set. This is your Q, and this is your Q bar. Now we have what is known as a counter. The counter will generate my D0, D1, etc. You will study about this concept of counters soon, but we are currently using this because it simplifies it. Okay. So let us run it. So this is your Q. Q is your output. It can't be minimized, unfortunately. So Q is your output, and this is QC. R is your reset, S is your set. So S and R both are 0. S and R both are 0. What happens? Q remains as it is. Next, Q was 0, it stays at 0. Now S is still 0, R is made 1. So Q has to be 0, it becomes 0. Now S is made 1, R is made 0. So Q becomes 1. Next is a condition where S and R both are 1. Okay? And you will see that the output is not properly defined. And let us see. Which tool, some count. Oh, okay. Run it for 10 microseconds. So S is 0, R is 0, Q is 0. S is 0, R is 1, Q is 0. S is 1, R is 0, it remains, Q becomes 1. Okay, so Q is 1. Very good. Now S is 0 and R is 0, but Q remains 1. Q remains 1. Because in the truth table, if S is 0 and R is 0, Qn plus 1 will be same as Qn. So it remains like this. Then R is made 1, S is made 0, so Q it is reset. Then S is made 1, R is made 0, then it will again be set. And when S is 0, R is 0, it again stays high. Next, R is made 1, S is made 0, so it goes low and again it goes high. So this is how it will proceed. Okay. So this is regarding the SR flip-flop, SR latch. So this is how the SR latch can be done. But there is a issue with this implementation. What is the problem with this implementation is it is level triggered. Since it is level triggered, what happens is it depends on S and R. So if S and R, they abruptly vary, then Q also will vary like that. So in case, there is certain noise or spikes or delay, it would, really impact the performance. Okay. So what is done is you have a triggered flip-flop. If it doesn't have a clock, it is known as a latch. But when you add a clock, it becomes a flip-flop. Now we'll consider a triggered flip-flop. You already know that there is this NOR gate here, right? Again, this NOR gate is there. This is your signal. This is your signal. Q bar is fed like this here. This is fed like this here. Fine. Now we will have an AND gate. Okay. This is your set, which was your original, and this is coming from another circuit. This is an AND gate. Sorry. An AND gate over here. This is your R, and this is coming here. Okay. And what is the signal? This could be enable signal. It could be an enable signal. If it is an enable signal, then it is known as a edge trick. It is known as a level trigger flip flop. But what we want is we want a transition with generator. So you will have your clock over here. Your clock will be of 50% duty like this. But this signal PT will be like a very small pulse. Very small pulse. So when this goes high, that time your PT also will go high. Okay. This is known as your PT. This is generate. So what this will do is it will be a positive edge triggered flip-flop. Only in the positive edge, the value can change. So what is the current value of S and R at the instant when the positive edge trigger comes of your clock, then your flip-flop value will be set. Okay. Similarly, you can have a negative edge triggered flip-flop as well. Okay. Now, the problem with your SR flip-flop was your S is equal to R is equal to 1. This is forbidden. This is not allowed. So what is done in that case is you have the same circuit, only you send it is just a D. Just D. Here this was an AND gate, and then this is what was your previous SR flip-flop. Right? What is added is a NOT gate. So this comes from your clock, which has that pulse generator, everything. And this goes over here. Okay. So this was initially your S, this was initially your R. Now your R is equal, so S is made equal to D and R is equal to made D bar. And this is your Q. So if you will look at this circuit, you would know what you would know. If your S is 1, then your R has to be 0. That is what you say. You have S, you have R, you have QN. So there are only two options. Either S is 1 and R is 0, or R is 0 and S is 1. So if S is 1, that means what? Qn is 1. If R is 1, that means what? Your Qn is 0. And what is your input D? D is dependent S. So this is 1 and this is 0. Okay, this is your Qn plus 1. So your Qn plus 1 is equal to D. So this is known as a D flip-flop. Okay. Now there are certain additional things. So how do we represent the D flip-flop? Here you have D. Over here you have your clock. Over here, D is the input coming here. C is there. Here you have your Q, and this is your Q bar. Now, when we do certain things, we really love to start our day well. We really like a circuit or any system of ours to start from one particular important point. From a point where we consider it should start, it should begin. So for that, we need to be able to control this Q. You need to be able to control this Q. So D, so if you see the circuit, this equation, D can control your Qn plus 1. But Q0, you cannot control Q0. So to do that, there is something called preset. Preset is added and there is something known as clear. So if preset is 1, what will happen? It will make your Q0 to be equal to 1. If your clear is 1, it will make your Q0 to be equal to 0. So basically what you're able to, you're able to initialize the circuit as per your required condition or your requirement. So this basically you're able to set the initial condition. Okay. So this PR and CLR, these are asynchronous because they are not dependent on the clock. That is, you see in your previous circuits, what happens? The input S and R is ANDed with the clock pulse, right? But here in this case, this preset and clear, they are independent of the clock. So that's why they are known as asynchronous. Okay. Now this another very popular flip-flop that is known as your JK flip-flop. How is JK flip-flop constructed? It is also made using the SR flip-flop. This is your Q bar. This is your AND gate, right? This is your input J, and this is coming from your clock. This again is coming from here. This is your input K. Now, we're taking the feedback of Q over here, and the feedback of Q bar goes over here. So that is why in this truth table, there is no condition that, S cannot be equal to 1, R cannot be equal to 1. Both together cannot be 1. That condition will be prevented. And we'll get a new truth table. So what does this truth table mean is, if this is your clock and you have J and K, and we are trying to find what is Qn plus 1 and what action is being happening. If your clock signal comes and at that instant your J is 0, K is 0, then what will be your Qn plus 1? Qn plus 1 will remain as Qn. Okay, there will be no change. But when the clock comes and your J is 0 and K is 1, then your Qn plus 1 will become equal to 0 irrespective of whatever was the previous Qn. So basically this action is known as the reset action. Okay, it's basically the reset action. Now, if the clock comes and the input J is 1 and K is 0, what will it do? It will set. It will make the output Qn plus 1 equal to 1. And basically this is the set operation. And then if the clock comes and your J is 1 and K is 1, then your Qn plus 1 will toggle. It will become Qn bar. So basically this operation will toggle your previous state. Okay, it will toggle your previous state. So this is permitted. This is permitted in the case of JK flip-flop. And JK flip-flop is constructed from your SR flip-flop by making a slight required desired modification. Okay. So these are the various flip-flops which we have considered. Now, we will consider how do you represent flip-flops. So every time we cannot, check what is K, what is J, and every time we cannot see the output. J may change, K may change, various other functionalities might occur. So we need to get, what is the, we want to, mathematically define what is the behavior of that circuit. So let us see for an SR flip-flop. How can we write what an SR flip-flop does, how it does it? So we have an SR flip-flop. Okay. You have S, you have R, you have Qn, and we have to find what be Qn plus 1. So again, as the truth table, which is the standard truth table, which we have been writing for the last 6 to 7 weeks, let's consider it. That is because it's a 3 variable one, so it will have 8 entries. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Now, S is 0, R is 0, Qn plus 1 will be same as Qn, so it will be 0. And Qn is 1, then it will be 1. But if S is 0, R is 1, whatever may be Qn, the output will be 0. So it is 0, 0. If S is 1, R is 0, then output will be 1, 1. So it is 1, 1. If S is 1, R is 1, the output is not defined. So we mark it as X. We mark it as X. So when you look at this, what rings bells would be, your K-map. How would the K-map look of this? Let us draw the K-map. So we have SR and we have QN. Okay. SR is 0, 0, 0, 1, 1, 1, 1, 0. QN is 0 and 1. Okay, let us draw it. Let us implement it. So if SR is 0, 0, Qn is 0 and 1. If SR is 0, 1, set is 0, R is 1, so it is 0, 0. SR is 1, 1, then it is undefined. If SR is 1, 0, it is 1, 1. So now we have to find the K-map of this, K-map representation. So what do? We can combine this, right? We can combine this and we can combine this here, right? So we get Qn plus 1, that is equal to your S, Ks plus this other second one. Second one is Qn and R bar. Qn and R bar. Okay, so this is the equation for SR flip-flop. From the truth table, we found what is the characteristic equation of the SR flip-flop. We can also do it for various things, that is the JK flip-flop. Okay, let us consider JK flip-flop. You have J, you have K, you have Qn, you have Qn plus 1. So again, you have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, if J is 0, K is 0, Qn plus 1 is equal to Qn, so it will be 0 and 1. If J is 0, K is 1, it is reset, so it is 0, 0. If J is 1, K is 0, it is set, so it is 1, 1. If J is 1 and K is 1, Qn will toggle, so 0 will become 1 and 1 will become 0. Okay, so now let us draw this K-map. So when you draw this K-map, what do you have? You have JK here and you have Qn here. Okay, this is 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. When both are 0, it remains 0, 1. 0, 1 means it is 0, 0. 1, 0 means it is 1, 1. And if it is 1, 1 and 0, it is 1, else it is 0. So we have got this. Now, how do we write it? This is one map, one combination, one product of sum, one product term, and this is another term, right? So your Qn plus 1 would be equal to, what's the first term? It is Qn bar and S. Not S, it is J over here. It is J over here. Qn bar and J. And the next term is what? Qn and K bar. Qn and K bar. Okay. So this is the representation of your, this is the characteristic equation of your JK flip-flop, which you will be using a lot in the upcoming tests, upcoming questions and all, which you will be solving. Okay. Next, we can have, so one is we are seeing the inputs and we are determining the outputs. This is through the truth table, this is through the characteristic equation, etc. But what if we observe the change in outputs? We observe the outputs and we can assess the inputs. Like what would have been the input What could have been the possible input? What is the next possible input? What was the change in the input? Or has the input remained same? Or has the output remained same? All that. So that is known as a excitation table. Excitation table is what is used. Okay. So how do we write the excitation table? Let us look in for the JK flip flop. JK flip flop. Or we'll consider for JK flip flop. So now what do we have is we have Qn and we have Qn plus 1. And then we have to find out what would have been the possible J, what would have been the possible K. Like it's kind of like reverse engineering. We're seeing outputs, then we are trying to understand what are the inputs. We know what is the circuit inside the black box, that is your JK flip flop. But we are observing the outputs and we are trying to estimate what could have been the possible inputs. Okay. So one is Qn could have been 0 and Qn plus 1 is 0. Qn could have been 0, but Qn plus 1 could be 1. Qn could be 1 and Qn plus 1 would become 0. And Qn could be 1 and Qn plus 1 could remain 1. Okay, it could remain 1. So what possibility do we have? Now Qn is 0 and Qn plus 1 is 0. That could mean your J could have been 0 and K could have been 1. If that case means what is happening is the reset action is happening, and since it is already 0, it will remain 0. But if J was equal to 0 and K was equal to 0, it remains at its previous value. And if the previous value was 0, Qn plus 1 also is 0. So there are two conditions. So J has to be 0, but K could be 1 or K could be 0. That is why it is marked as an X. It is possible. It could be 0 or 1. So that means if your Qn is 0 and Qn plus 1 also is 0, then what could have been the possible inputs? One is you have applied inputs J equal to 0, K equal to 1, such that you're saying that telling your flip flop you must reset. So if it was already 0 and you say you reset, it will still remain at 0. So that is one condition. Next is you could also have a possibility that J is equal to 0 and K equal to 0. That means you're telling the flip flop whatever previous condition Qn you have, you retain that condition. So that means Qn plus 1 also should be equal to Qn. So that means J equal to 0 and K equal to 0. This is a possible input, or J equal to 0, K equal to 1. This is also a possible input. So in both these cases, J is 0. So you replace J by 0. And K could have been 1 or K could have been 0 as well. So it is marked as an X. Okay, it is marked as an X. Now, we have, what do we have? Qn is 0 and Qn plus 1 is made 1. That means we could have had J equal to 1, okay, and K equal to 0. This would mean you're setting the flip flop, so it is going from 0 to 1, or it is becoming 1. Also, you could have J equal to 1 and K equal to 1, right? What does this mean? This means you are toggling. You're toggling. It was initially 0, now you're making it 1. You're doing toggle operation. So if you see this, what do we assess? J has to be 1, but K could be anything. K could be anything. K could have been 0, K could have been 1. Similarly, we'll consider this case. Qn is going from 1 to 0. 1 to 0 means again your J equal to 1, K equal to 1 could be possible. That means you're toggling it, right? Or your J equal to 0 and K equal to 1. That means you're resetting it. Both could have been possible. So that's why J is anything, K in this case is 1. K in this case is 1. Now your next condition is you're going from 1 to 1. This can happen when your J equal to 0 and K equal to 0. That means you're telling it to remain as it is, to have no change. State should not change. Or else you are setting it. So J could have been 1, K could have been 0. Right? J could have been 1, K equal to 0. So then you see J could be any of these conditions and K has to be equal to 0. Okay, so this is for this condition, this is for this condition. So this is known as the excitation table. That how are you going? That you're observing the outputs. Then you're trying to understand what could have been the possible inputs. So this is known as your excitation table. Okay, now we are all, especially men, we are all very visual people. So we like to understand when we see diagrams. So let us think. So you have 0 and 1. Okay, that means this means your Q, your this means what? Your Q is 0. This means your Q is 1. So now if I want to go from 0, I want to come back to 0. Then what could be the possible? J could be 0, K is 0, or J could be 0, K is 1. So we could have what conditions? J 0, 0, K 0, 1. Similarly, I have a condition that I'm at 1. I have to again go back at 1. So what do we have? J could be 0, 0, and JK could be 1, 0. This is also a condition. Next, I am at 0. Okay, I'm at 0. I want to go to 1. That means I'm going like this. So what could be possible in this case? My J could be 1, K could be 0, or J could be 1 and K could be 1. This is a condition. Similarly, I am at 0 and I want to go to 1. Sorry. I am at 1 and I want to go to 0. That means I'm going from 1 to 0. So what could be the possible inputs? J could be 0 and K could be 1, or J could be 1 and K could be 0. So this is known as your state transition diagram. How are you migrating? How is it going from one state to another state, or how is the evolution of the state? Okay, that is shown by what is known as your state transition diagram. State transition diagram. Okay, all right. So now we look into certain assignment questions of the previous year. We'll try to understand what they mean, how do we solve it, and we'll move ahead. Okay. So this is the question 1. So it says which of the following are the characteristic equations of the JK and SR flip flop? So for the JK flip flop, what do we know? Qn plus 1 is J into Qn bar plus Qn and K bar, right? That is J into Qn bar plus Qn dot K bar. And for the SR flip flop, what is the characteristic equation which we have derived just a few minutes back? Qn plus 1 is equal to S plus Qn dot R bar. Okay? S plus Qn dot R bar. So out of this, which is the correct option? The correct option is A. Because Qn plus 1 is Jn and Qn bar plus Qn and Kn bar. And then for SR flip flop, Qn plus 1 is S plus Qn into R bar. Okay, that is the correct characteristic equation. Okay, we'll go to the next question. This is the truth table of a hypothetical AB flip flop. Find its characteristic equation. Question 2. Okay, we have to find. We are given a hypothetical AB flip flop. It is a flip flop which we have never studied. We have not heard, but we have to find its characteristic equation. Just hold on 1 minute. Okay, sorry, excuse me. There was a plane flying over, so it was very loud. Okay, so now we have this truth table and we have to find the characteristic equation. So how do we do? So this is in the extended variable form, which we had studied previously. So we have to find Qn plus 1. So what is Qn plus 1? So let us write Qn plus 1. We'll consider this. What is it? It is A bar and B bar and 0. Then next we'll consider this line plus A bar and B and Qn. Then we'll consider this line, which is what? A and B bar and Qn bar, right? Then we'll consider this line plus A and B and 1. Okay, A and B and 1. So basically, what do we get then? We get our Qn plus 1 is A bar and B and Qn plus A and B bar and Qn bar plus A and B. Okay, it looks big. So what do? We can try to do algebraic simplification. So how do we do algebraic simplification? Let's see. So this is A bar and B and Qn plus A and B bar and Qn bar. We don't touch this. This 1, which is over there, we represent it as Qn plus Qn bar in a bit to simplify. Hmm. So what do we get? This A bar and B and Qn plus A and B bar and Qn bar plus A and B and Qn plus A and B and Qn bar. So what do we get? We get A bar plus A and B and Qn plus A and B bar or B and Qn bar. So since what are we doing? We are exploiting the property that x plus x bar is equal to 1. This is the property being utilized or incorporated. So what do we get? Our Qn plus 1 is equal to B and Qn plus A and Qn bar. Okay. So this is how we can write the characteristic equation of the hypothetical truth table. So what do we did? We looked at the truth table, which was in extended variable form, and then we substituted the values. We got a little bit long, big expression. Then we did use Boolean algebra and we simplified the expression. And we got a smaller and a more compact representation, that is B and Qn plus A and Qn bar. Okay. Right. We'll go to the next question. We look here. So question 3. So what will be the simplified expression in the next state Q? So that is, they're asking what is Qn plus 1. What is Qn plus 1? Now you will notice you have an SR flip-flop. And you'll notice that, let us say this intermediate variable here. This is variable with value m. That means your S is equal to m bar, Sn is equal to m bar, and your Rn is equal to m. Okay, Sn is equal to m bar, Rn is equal to m. So what does this do is it makes sure that Sn equal to Rn. It doesn't allow it, doesn't permit it to happen. And this is done by this circuit. Okay, so what is M? M is Qn x nor of x. So M is Qn x nor of x. Right? This is your x, this is your Qn. So now, how do we further simplify? We know Qn plus 1 is equal to Sn plus Rn into Qn bar. This for an SR flip flop. Right? So Qn plus 1. What is Sn? Sn is M bar. What is Rn? Rn is M and Qn bar is Qn bar. It remains as it is. Right? Mm. Sorry, there's a mistake here. For the SR flip flop, it means the rubber. Qn plus 1 is Sn plus Rn bar and Qn. That means Qn plus 1. Sn is what? M bar. R bar is M bar and Qn. This is what M bar and 1 plus Qn. This is equal to M bar. Okay. So M is Qn dot x naught x. So M actually is Qn x or of x bar. Therefore, M bar is equal to Q XOR X. So that's why Qn plus 1, which is equal to M bar, it is equal to Q XOR X. Okay? This is the circuit. Okay. Let us consider this for a gated D-latch. Question 4. So we have to identify what is correct for a D flip-flop, right? One is the output follows the input when enabled. The output toggles if one of the inputs is high. No, this is for a T flip-flop. The output complement follows the input when enabled. No. So this is correct. The output follows the input when enabled because Qn plus 1 is equal to D for a D flip-flop. So if it was a latch, also it would follow the same example. So that's why Q is equal to D for a gated D latch. Okay, we'll go to the next question. This is question number 5. So it talks about what is known as a master slave JK flip flop. So what does a master slave JK flip flop do? Basically, it has a master flip flop like this over here, and there's a slave flip flop. Which is the SI flip flop. Now there's an enable signal. Enable signal. When this is enabled, what it is, the other flip flop is disabled. This is your input. So basically, an enable also is coming at the rate of the clock, right? So half the time, the 0 to T by 2 is working as a master, the master flip flop part is working. And the next half the time, that is from T by 2 to T, this part is working. The slave flip flop is working. Okay. So let us see. We went diverted. Let us go back to the question. So master slave JK flip flop, which statements are correct? The toggle frequency is the maximum clock frequency at which flip flop will toggle reliably. Yes, that is true. The data input must precede the clock, triggering the transition edge transition time by some minimum time. Yeah. If we are reading some data, this must have some minimum width. Right? And if we are reading the data from here to here, it will not read. It should be within the time and it should also be of that sufficient duration. Data input must precede the clock triggering edge transition time by some minimum time. True. The data input must remain fixed for a given time after the clock triggering edge transition time for reliable operation. Yeah. Because we cannot have the case where the data input is faster and the output is slower. The output is faster and the data is slower. That is not allowed. In these in these sequential circuits, what we do, we consider there's a same master clock, which is being fed to all the modules like we consider for the master slave clock, etc. The same clock, it can either be enabled or disabled, and means the options are there. You can create a positive edge trigger, it can create a negative edge trigger, it can be used for these sort of edge trigger flip flops and latches, or it can be used for these expensive latches, basically connected. Expensive latches, okay. So we are going to consider this question. For a circuit which is activated when the clock signal goes from low to high, what is it called? Is it called positively edge triggered? Is it negatively edge triggered? Is it neutral edge triggered? Or is it dynamic edge triggered? Specifically told it is going from low to high. So that means it is positively edge triggered. Okay? It means it is positively edge triggered. Next, we have some sort of challenging question for us to think, use our heads, and try to understand how the output will look, and so on. And if time permits, we will try to simulate it and to see the outputs as well. So now you you have studied for one flip flop. You have studied SR flip flop, JK flip flop, D flip flop, T flip flop, but you have considered one flip flop, how it behaves. But how do you know? Like there's a set of flip flops. So you have a system. A system will not just be one flip flop. It's not the point. You have a set of flip flops, and you want to check how the entire overall circuit will behave. So what you have to do, you have to assess the input and the output to each of the flip flops, see what is happening, how it is changing, and then you can get the output. Okay, so you also it's just basically a combination of flip flops which forms a sequential circuit, and we will look into. So now we have four flip flops. These are all D flip flops. You can see what is it, and all the flip flops in the following circuit are initially reset. All are reset means what? This is zero, this is zero, this is zero, this is zero. You should not get confused that this is S, this is R, this is T, so it is SR and T flip flop. No, all of them are D flip flop. Q and Q bar are the outputs. So this Q, R, S, T are outputs of the D flip flop. So it removes that confusion. Now, output, what you have to do is, after which clock signal is triggered continuously. So you have a clock which is coming continuously. You have a clock which is coming continuously. So you need to know how your output Y looks. What you must understand, your output Y will be low, it will go high, it will be low, right? And then again it will go high. So this is your time, and that how many number of cycles is uh, n cycles, and this time for which it is on is m clock cycles. So you need to find out what is the time duration. And this, if you know, if people are very well versed with this, it is kind of like a pulse width modulation, where you have a fixed frequency, but you're modulating the pulse, the duration of that pulse. So this will just try to understand what this output looks like. You're basically, you're slowly, being exposed to sequential circuits so that you can understand how they work. You can look into it. You can try to reason with it. You can, from the basics, maybe clear. Okay. So there is, when you're analyzing these kind of sequential circuits, there's a problem is there's a delay, there is history. So you have to incorporate that. So if at all it is not mentioned in your question, you should assume that your outputs are all reset. But if as it is mentioned, you assume it is reset. But if it is mentioned that Q was 1, R was 0, S was 1, T was 0 or something, you have to accordingly, you have to change it. Okay, so you will have to look into it. So now let us try to understand. So you have the clock. This is the first clock. This is the second clock. This is the third clock. This is the fourth clock. And how many variables you have? You have four variables. What are the four variables? You have Q, you have R, you have S, you have T. Okay? And you have Y. So what is your Y? Let us try to understand. Y is equal to T bar and Q bar. Okay, Y is equal to T bar and Q bar. So now let us assess. So you have QRST. It was all 0, 0, 0, 0. All are 0. Okay. As per the thing, Y is equal to T bar and Q bar. So Y was 1. Y was 1. So this was when the clock was 0. But now we'll see the first clock. It gets triggered. It is edge triggered. The first clock has come. Well and good. Now what happens? Q's input, if you will see. What is the input for this D flip flop Q? That is T bar. What is T bar? T was 0, so T bar is 1. So Q becomes equal to 1. For R, what is the input? R's input is Q. Q was 0, so that's why this becomes also equal to 0. S, the input is R. R was 0, so it also becomes 0. For T, the input is S, right? So that also becomes 0. Now what happens to Y? Your Y is T bar and Q bar, and since Q bar is 0, so that means Y becomes 0. This is the first clock pulse. Now then, next clock pulse. Next clock pulse, what happens? Your D is again T bar. T bar is 1, so that's why Q becomes 1. Your R is Q, so that's why it becomes 1. Your S is R, so that's why it becomes 0. Your T is S, so that's why that also becomes 0. Now what is your Y? Y is T bar and Q bar, so that is equal to 0 again. Okay. Now let us go to the third condition. Because let us say Q is dependent on T bar. R is dependent on Q. S is dependent on R. And T is dependent on S. So that is what we are trying to understand. Now, Q is T bar. T bar is again 1. This is 1. R is dependent on Q, so this is 1. Right? S is dependent on R, so it becomes 1. So basically, it is going like this. It's going here like this, like this. And this one bar is coming over here. Right? Similarly, T is dependent on S, which is 0. And Y is what? Q bar and T bar. So that is also 0. Now, the fourth clock pulse comes. And Q is again T bar, so it becomes 1. And it proceeds to become 1, 1, 1, 1. In this case, your Y again is 0. Y is again 0. Now the fifth clock pulse comes. And now Q is equal to T bar. T bar has to be 0. And R is Q, so 1. S is R, so it is 1. T is S, so it is 1. And what is your Y? Is this Q bar and T bar? T bar is 0. So that's why this also is 0. Now let us go to the sixth clock cycle. So Q is T bar. T bar is 0. So this becomes 0. R is Q, so it will become 0. S is R, so it means 1. T is S, so it is 1. Now what is Y? It is again Y is Q bar and T bar. Q bar and V is 1, but T bar is 0, so this again is 0. So now let's go to the seventh clock cycle. Seventh clock cycle, what happens is your Q is T bar, so that means again it is 0. R is Q, so it is 0. S is Q, S is R, so it is 0. T is S, so it is 1. So T bar and Q bar, so this again is 0. Right? Now let us go to the eighth pulse. We are going to the eighth pulse now. Now T bar is 0, so this becomes 0. Then they all are passed forward, and your Y will be equal to 1. Y will be equal to 1. So now I want you to see, like can you keep on going? It will keep on going because your clock is going to come indefinitely. It will come. And your output and your input and your states and your condition, all of them keep changing. What you have to observe as an engineer, as a one who's analyzing the circuit, you have to understand the pattern when the pattern is being repeated. It's a sequential circuit, it's a periodic circuit, it is being repeated, It is not like generating any number of bits randomly. There is a sequence, there is an order and everything. So you have to find when it is being repeated. So if you will observe that what did we consider that the circuit started at rest? That means Q was at 0, R was at 0, S was at 0, T was at 0. Now, the circuit, what happened? You gave clock. The bits got changed, updated, dependent on the connection, everything, the bits changed, it varied, all that happened. Then finally, again, you have come to a condition where again you have Q is 0, R is 0, S is 0, T is 0. Now, you assume you added a ninth pulse. What will happen now? Since it is a fixed hardware, the circuit is fixed, it would only be 1, 0, 0, 0, and 0. So again, the output will, again, the bits will change accordingly. And the sequence will be repeated. So that's why it is repeated after 8 clock cycles. It is repeated after 8 clock cycles, right? Now, you must find out for how many clock cycles it is high. So out of all your 8 clock cycles, only 1 clock cycle it is high. So it is high for only 1 clock cycle. Okay, it is high for only 1 clock cycle. So let us go for the next circuit. Just one. Question 8. So what you must understand is when you will be giving the NPTEL exam, you will not be told that this is an SR flip-flop. This circuit is a SR latch. This is this circuit. This is that circuit. You must remember this concept. You must understand the concept. What you'll be given is you have gone through this entire 12 weeks of heavy digital content. You would have learned many things. You would have understood many things. You would have given all the 12 assignments. You would have done this AI generated assessments also. You would have done. You would have done various things. But you will, when the question paper comes, you will not know that this question is from week 2 and from this part, so I must use this formula and I must understand. What you must learn is you must have that intuitive approach. You must try to understand the question. You must see what is given, and from this question you must find a hint. Okay, that this is related to this concept. And when this part is being told, it means that there is some trick over there. There's something which the person who has framed the question, he wants me to understand it. And when I understand it and I understand and I find a solution, it proves to the person who set the question paper that I have understood that particular concept. So it is testing my knowledge of the concepts. It is like applied knowledge. Okay. So what is given? They say A is 1, B is 1. And if you see the gates, they are NOR gates. They are NOR gates. So what is a NOR gate? What is the truth table of a NOR gate? Like it is the truth table. Okay. You have this inputs, you will get this output. That is fixed. Okay. Life is not like a truth table that if you do work hard, do this, do that, then you'll be successful. It is not like that. But in terms of these logic circuits, when we are analyzing it, we assume that it is a truth table. So what do we have? NOR gate truth table is what? You have input 1, you have input 2, and you have an output. This is NOR gate, 2 input NOR gate. We look into it. So as it's a two inputs are there, the truth table will have 4 rows, 4 entries. So 0, 0, 0, 1, 1, 0, 1, 1. Now, or in an or, if there is a 1, it will output will be 0. Output will be 1. But in NOR gate, if there is any 0, the output is 0. So this is 0, 0, 0, 1. No, sorry. If any of the input is 0, the output will be 1. Okay, so this is 1, 1, 1, 0. So this is the condition. So what you have told that A is 1 and B is 1. So if A is 1 and B is 1. Now, they're saying A is 1, but B is simply 1, 0, 1, 0, 1, 0, 1, 0. So that means what they are considering, they're telling us, look at this, look at this. They're saying A is 1. That means A, this is 1. So they are considering this circuit. So A, this is your A. And now this will be your B. So when you look at it, what you say, if I have fixed A is 1 and now B is 0, then what is the output? It is 1. That is, it is B bar. And if B is 1, then your output is 0. So that is again B bar. So that means your output P, in this case, what would it be? Okay, we have to look into it. So A is 1 and you are giving anything. If you give A 1 and you give anything to your NOR gate, it is also dependent on Q, right? Because it's a NOR gate. A is 1 and B is 1. So it could be something random, right? It could be something random. So let us say A is 1 and B is 1. Then we are, so A is 1, B is 1. EQ could be anything. Okay, the issue is the blunder is in my side. I apologize. So not truth table is 1, 0, 0, 0. This is a not truth table. So if you have 1 as an input, your P will become 0. Okay, 1 as an input, P will become 0. Okay, any one. Now if B are 1 is, then Q becomes 0. But if your B is 0, then you get 0 or 0. 0 or 0 means 1, so it is 1. Now then, next what happens? This becomes 1. If this becomes 1, this is always 0. So 1 or 0 will become 0. Then if B becomes equal to 0, then the output will be 1. So that means P will always be 0, but Q will be equal to B bar. Okay, Q will be equal to B bar. Okay. So whose operations are faster among the following? So you have combinational circuits, you have sequential circuits, you have latches and flip-flops. So in combinational circuits, this is the input, this will be the output. It's a truth table based approach. Sequential circuits, you have a delay. With combination circuits also you'll have delay, but it is lesser. In it's not exactly lesser, but we can say there's a delay. But in sequential circuits, you have a clock. It is clock dependent, right? Clock dependent. In latches, though it doesn't have clock, still it requires feedback of output, right? You are giving inputs, but in addition, you have feedback of outputs. And flip-flops, it is what? It is clock dependent, as well as it has feedback, everything. But in combinational circuits, you're just applying inputs. You're just applying inputs. So basically, how much delays to the gates, that is only what is limiting your combinational circuit. So among all these four, the fastest would be your combinational circuits. Okay, combinational circuits also we love. It is very easy for us to understand and everything. But there are certain scenarios, there are certain cases where you want a dynamic operation, dynamic behavior, and to do all that, we need the sequential circuits. Okay, so everything has its place, everything has its pros and cons, but you need to learn to identify where combinational circuits are needed, where in which condition these sequential circuits will be more useful, will be more better, or in which condition sequential circuits alone can perform that particular operation and all that. Okay, so that comes to you're going through this wonderful digital electronic course, and we hope that you would become really strong and well versed with this digital circuits. So now we again have a D flip flop. So D flip flop is like used a whole lot, and we want to find it will generate a sequence, and you have to find what sequence is it generating. Okay, so these are circuits which are very easy, which are very interesting. It uses logic, so you need to carefully understand what is the cause, what is the behavior, cause and effect, what is the outcome. All this you have to understand it. Okay, but this is an engineering perspective, so it doesn't change much. It's not that much of heuristic. It's more structured. So this is question 10. So basically, this is what it has 3D flip-flops. And what they have told us, the initial state they have given us, it is 0, 1, 0. Clock period is 40 nanoseconds. Transition takes place at the rising edge. Okay, transition takes place at the rising edge. So this is your clock. What is the rate of the clock? Also, they given 40 nanoseconds. 40 nanoseconds, if I'm not wrong, 40 nanoseconds. This is your T clock. So your F clock would be equal to for 25 megahertz. Okay, F clock is 25 megahertz. So at that rate, your clock is coming 25 megahertz. So fast. All right. Now for the D flip flop, what do we know? We know Qn plus 1, that is equal to your D. Qn plus 1 is equal to D. Whatever input you give, that is the value you will get. But this should happen only at the transition. Okay. So what is your D0? D0 It's coming from here. This is a feedback is there. So D0 is equal to Q2 bar. What is your D1? D1 is equal to Q0 bar. And what is your D2? D2 is equal to Q0 and Q1 bar. This Q0 and Q1 bar. So let us try to know what is happening, how it is happening, how do we proceed, right? So we'll have Q0, we have Q0, Q1, Q2. What do we have? D0 is Q2 bar, D1 is Q0 bar, and your D2 is Q0 and Q1 bar. So initially, what do we have? Initially, we have been told that Q0, Q1, Q2 is 0, 1, 0. 0, 1, 0. So what is the value of D0 at that case? D0 in that case would be 1. D1 in that case would also be 1. And D2 in that case would be equal to Q0 and Q2 bar, so it is 0. Now, your clock comes. Your clock comes. When the clock comes, Q0 will take what is D0, so it will be 1. Q1 will, so it will go like this, will go like this here. Q1 will take what is D1, so it will become 1. Q2 will take what is D2, so it will become 0. So it is 1, 1, 0. Now, once this has changed to 1, 1, 0 and the clock has gone, what will happen to D0 and all? D0 will become Q2 bar, that is 1. D1 will become Q0 bar, that is 0. And D2 will become Q0 and Q0 and Q1 bar. So that is again 0. So it is 1, 0, 0. Next, another clock will come now. So what will it take? It will take the values of D0, D1, D2. It becomes 1, 0, 0. And when these Q get updated, your D also will change at that time. So D will be Q2 bar, that is 1. D1 will be Q0 bar, that is 0. D2 is Q0 and Q1 bar, that is 1. Okay, there is 1. Next, the next clock comes. So this D0, D1, D2 get passed to Q0, Q1, Q2. So it becomes 1, 0, 1. Now your D0 becomes what? It is 0. D1 becomes what? It becomes 0. D2 becomes what? It becomes 1 again. Right? Now again the clock will come. Then when the clock again comes, whatever values were there, it gets passed back. So it becomes 0, 0, 1. Now D0 is Q2 bar, it becomes 0. D1 is Q0 bar, it becomes 1. D2 is Q0 and Q1 bar, it becomes 0. So it is 0, 1, 0. Now again another clock comes. Then these same values get passed to you. That is 0, 1, and 0. Okay. Then what happens? This becomes 1, 1, 0. So what do we see? This was where it was initially. Now it is again gone over here. So how many clocks it required? 1, 2, 3, 4, 5 clocks it required. It required 5 clocks were needed. Now we have to draw what is the state transition diagram. So it goes from what it goes from 0, 1, 0. Then where does it go? It goes to 1, 1, 0, right? Then where does it go? It goes to 1, 0, 0. Then it becomes what? It becomes 1, 0, 1, right? Then it becomes 0, 0, 1. So this happens in the first clock, second clock, third clock, fourth clock, fifth clock. So totally for this, this is a repeative sequence. How many clocks are needed? It needed 5 clocks. Okay, so 5 clocks means 5 into 40 nanoseconds. 5 into 40 nanoseconds will become 200 nanoseconds. So what is the rate? What is the rate of which your signals, your bits are changing? Is 1 upon 20 nanosecond, 1 upon 200 nanosecond. That comes out to be 5 microsecond. Right? 5 microsecond. Okay, so this is the update rate. Not 5 microseconds, sorry. 5 into 10 to the power 6 times. or basically this is 5 megahertz. So your update rate is 5 megahertz. The rate at which the state transition diagram is just transitioning from one cycle to finishes its periodic behavior to the next, that is 5 megahertz is the update rate. Okay. So there's a very interesting thing. You have a combination of flip-flops, and then you try to understand what is the sequence, what is the output. You learn it is edge triggered. You assess all of that. You know what is the initial condition. You know what is the rate, and then you can make the table how the sequences are being generated. Then you can draw the state transition diagram, and you can proceed. So it is a step-by-step sequential manner in which you have to actually answer these questions. Okay. Now we go to the next question. An XY flip-flop is given there, and you want to implement it using a JK flip-flop. So this is the question 11. So you're given the characteristic table or truth table of an XY flip-flop. Okay. It is a flip-flop. Now you have to make this flip-flop using a JK flip-flop. How do you do it? So you have Qn plus 1. Qn plus 1 is equal to what? X bar and Y bar and 1. This part. Then here you will represent it as X bar and Y and Qn. Then what you'll represent over here, it will be X and Y bar and Qn bar. Okay, this is the representation. Now what you want to find Qn plus 1, and you want to make it a simple, easy expression. This is a bit advanced, and this is not what you can use to get a JK flip-flop. So let us write what is the truth table of a JK flip-flop. JK flip-flop is Qn plus 1 is equal to J and Qn bar plus Qn and K bar. So you want it in this format, but it is not in that format. So you have to make it into that format. So how do we make it into that format? We will use simple Boolean algebra and manipulation of the expression to get it into the format of a JK flip-flop. So what we have also previously considered, 1, we can write it as Qn plus Qn bar. I can write it. I'm not changing the truth of this expression. It is remaining the same. I am changing the form of the expression, but the truth or the output or the resultant of this mathematical Boolean algebraic expression remains the same. So I've written it in this form. Then I can write it this as X bar and Y and Qn plus X and Y bar and Qn bar. Then I expand this expression. So what it becomes X bar and Y bar and Qn plus X bar and Y bar and Qn bar plus X bar and Y and Qn plus X and Y bar and Qn bar. Now, it has become more complicated, but what did we want to do? We wanted to simplify it. So what we should do is we should appropriately group it in such a way. What do we want? We want Qn bar, and we also want Qn. So let us look at the expressions where we have Qn bar. So this is Qn bar. This also has Qn bar. This has Qn. This has Qn. So we have to group those things. When we want to group it, we must find what is common. So when we are trying to find what is common, what do we do is, if you see, X bar and X bar remains common here. So we write X bar and Y bar or Y and Qn. Okay, well and good. Next we have to do over here. Here what is common? You have Y bar is common and Y bar is common. So how do you write it as plus X bar or X and Y bar and Qn bar? So now let us write the simplified expression. It becomes X bar and Qn plus Y bar and Qn bar. This we have to come. So let us also write it better. This is Y bar and Qn bar plus X bar and Qn. Okay. When you compare this with J and Qn bar, plus Qn and K bar. What do we get? We get J is equal to Y bar and K bar is equal to X bar. This implies K equal to X. So you have to use J, you have to just put Y bar over there. You have to knot it. And for the K part, you have to give X. And if you do this, you would obtain this flip-flop. So using, one building block of a JK flip-flop, if you don't like the characteristic of JK flip-flop, it is not what is your desired method, desired output. So you can tweak it by certain, approximation, not approximate, by certain manipulation, by suitable arrangement of, combinatorial circuits in addition to the sequential circuit to get your desired output. Okay. So we have got this other X5 flip-flop also has been made using a JK flip-flop where we have exploited the characteristic equation of the JK flip-flop, which is very important for you to mark it and to remember it. Okay. So now let us consider this question where we are looking into another JK flip-flop. So this where the JK flip-flop is very popular with them. So let us try to understand how to go about this question. So this is question 12. So we have a JK flip-flop. So if you see what is J, J is equal to Q bar, huh? And K is equal to 1. So you have a clock there, you can give these pulses, right? So they are saying there are 6 pulses are coming. You have to find Qn plus 1. When you write it in terms of n and everything, what you write first is Qn is 0. Qn initially was 0. Okay, because they told the flip-flop is initially cleared. So Qn is 0. Now, your J is actually Qn bar. It is not of the future, it is of the present. So J is Qn bar. Now K is equal to 1. So now we know the characteristic equation of the JK flip-flop, which I also advise you strongly that you must remember it by heart. That is your Qn plus 1. It is equal to J and Qn bar plus Qn and K bar. Okay. So now let us substitute. So J again is Qn bar. So this Qn bar and Qn bar plus Qn and K is 1. So K bar is 0, Qn and 0. So basically your Qn plus 1 is equal to Qn bar. Okay. Now, initially what was Q? Q initially was 0. Then what happens? Your clock comes. So your clock comes. The clock comes, then Q changes from 0, it becomes 1. Again, the clock comes from 1, it becomes 0. Next clock comes, it goes to 1. Next clock comes, it goes to 0. Fifth clock comes, it goes to 1. Sixth clock comes, it goes to 0. So this is how the sequence of outputs you get. And if you look at the answer, this is what answer 1 0 1 0 1 0. This is the resultant you get. Because initially it was clear, then it is just basically toggling. So if you consider this JK flip-flop is being made to behave like a toggle flip-flop by setting J's Q bar and K equal to 1. So this is how you can convert a JK flip-flop into a T flip-flop. So there are these transformations from one flip-flop to another flip-flop. That is, if you only have D flip-flops, how do you connect it in such a way you can get a JK flip-flop and vice versa, and all these things are there. Okay. Basically, this is a T flip-flop where you are given 1. And as you know, in a T flip-flop, if you give clock, whatever is the output, it gets inverted. It gets toggled. So you have 1, the output becomes from 0 0, it becomes 1 1. Next, again, it becomes 1 0 0. Third clock comes, so let us write it. So So basically, this is a toggle flip-flop. What do you have? You have Q1 and Q0. What are the values? 0, 0. Now the first clock when it comes, values become 1, 1. The second clock comes, it becomes 0, 0. Third clock comes, becomes again 1, 1. Fourth clock comes, it becomes 0, 0. So that is what the output will become. What? Your 0, 0 is the output. Hmm. Simple T flip-flop logic. Nothing to, not too much, too hard to understand. Let's go to the next question. Again, this question is regarding a JK flip-flop, right? So how important it is for you to, try to clearly, carefully, properly understand the JK flip-flop. So many questions, it is easy to understand, easy to answer. So I recommend you to not skip this topic. Okay. So present output Q of an edge trigger JK flip-flop is 0. That is Qn is 0. You want to find Qn plus 1. What is it? You know for sure that J equal to 1. But K is unknown to you. So can you tell me what would be J? So let us go for the characteristic equation, which is very important. Qn plus 1 is what? J and Qn bar plus K and Qn, right? So what is it? It is 1 and 0 bar plus K and 0. So that means what? It is 1 and 1 plus 0. So it is 1. So I know as the next edge trigger, it would be logic 1. So this is simple. The way you get it is you should know this. If you don't know this, if like you have many things to remember, you have many subjects, everything, you you get to know the true table of JK flip flop. It is not difficult. It is just like the SR flip flop only when the condition is J is 1, K is 1, Qn plus 1 is equal to Qn bar. It just toggles. That is a simple condition. By now, you have practiced K map a whole lot of many times. So you have to, what you have to do, you have to find the K map, you have to find Qn plus 1 in terms of J, K, and Qn. You get that characteristic equation and you can solve many questions. Okay. So let us go to the last and final question of today. So this has been a Saturday. The session has been preponed, so you get more time to understand this topic. This problem solving doubting session has been conducted prior, so you can understand it and you can learn the concepts very well, right? So you can solve the assignments much ahead, and you should try to get full marks in the assignments. Okay. This is a AB flip flop. We have designed XY flip flop. Now we will design AB flip flop, and we have to find what will be the output. Okay. By now we should be very confident in how to handle this sort of question. So what is the Qn plus 1? It is equal to A bar and B bar and Qn bar plus A bar and B and Qn plus A and B bar, right? So again, it's the same concept. What do we have to do? This is and 1. We write it as A bar and B bar and Qn bar plus A bar and B and Qn plus A and B bar Qn plus Qn bar. You can write it. So this becomes equal to A bar and B bar and Qn bar plus A bar and B and Qn plus A and B bar and Qn plus A and B bar and Qn bar. So if you combine, what you will get A bar plus A and B bar and Qn bar plus A bar and B plus A and B bar and Qn. So this is what B bar and Qn bar plus A XOR B and Qn. Now let us represent in terms of the JK flip-flop, which we have studied many times. It is J and Qn bar plus Qn and K bar. So what do we get? J is equal to B bar, K bar is equal to A XOR B. So that means A continues to be B bar, no issue. But A from A XOR B, it becomes A XNOR B. Okay. And you have got the result. Okay. So congratulations. You have been able to solve this flip-flop part. Very interesting, intuitive. You can understand it. You can learn it. It is sequential. So it's really interesting and very nice to learn about these things. Okay. So now we have done all these things, right? We have tried drawing through timing diagram, understanding it. But let us why don't we just simulate it? Simulations are really a very nice, fun way to learn things. Okay, so let us try simulating it. So we have considered the SR latch. Okay. Now this is the simplest elements. Okay. You're new to it. You're new to the simplest elements things. You want to do digital circuits, you want to do. Simplest has so the simplest part has certain limitations in the number of digital circuits you can implement. Simetrix, I've read that it has lesser that you can do more. So let us go for Simetrix. So when you try learning a new software, you don't have to read up everything and know how it was made, what were the story, and that thing you don't need to know. A good software, which is popular and everything, what they'll have is they'll have certain example circuits. So if you do the example circuits, we understand the example circuits or the example demonstrations, and you can, tweak them according to your own benefit, then you can learn the software quick and fast, which is what is required in this day and age. Rapid, fast way, the technology is changing. And as a person, as a professional engineer, you also should rapidly update yourself. So for that, let's go to the examples thing. When we have downloaded it, there are certain examples which comes. So let us consider certain elements are there. Okay. You can have this. The digital devices, you can have a D-latch, you can have a D flip-flop, JK flip-flop, SR flip-flop. So let us go to the SR flip-flop. This is the SR flip-flop. Okay. This is a ready-made example they have given to us. Okay. And let us run it. It's just a demo. Hmm? You can see the outputs. I think they not make that much sense to you. Let me just look into it. So this is your SR flip-flop. Set and reset are set to 0. Okay. So that means the output is set to 0. Let us take it to, instead of digital, let us use a dedicated grid. Look better then. This is your R. Okay. This is your set. Hmm. This is your clock. We'll save it in our folder. Week 7 simulations. SR flip-flop. Okay. Just save. We cross out this diagram. Let me run it again. This is the output. So what does the output mean? What does it mean? Right? You have your clock. Okay, you have some clock. Let us change the time period. 20 micro. Let us make it 12 micro. Okay. Change the view. Okay. So this is your set pulse. This is your reset pulse. Your Q was 0. Then your set pulse goes high. So your reset is 0. Okay. There is a delay. there is a delay. That delay, because of the delay, your Q goes high after some time. Okay, let us do it in undock it. This will make more sense. Okay. So you have your clock. So in a flip flop, you have various clocks. Okay, you have various clocks are coming. Various clocks are coming. Okay. Now, what do you see? At this clock over here, when the clock is rising, okay, clock has risen. Okay, your set has become high, and your reset was 0. But at that sharp edge, at this sharp edge where it rises, your S was still low. It was still low. So that's why it doesn't change. That's why your Q remains as it is. Now, in your next case over here, when it is rising over here, okay, it is rising over here. That time what happens? Your S is 1 and your R is 0. So it has to go high. But there is a certain delay. A small amount of delay is there. Okay. Then again your next clock comes. Next clock comes. There's no change. So it remains high as it is. Then what do you have? Again this pulse comes. But your R goes high now. Your R goes high now. At this instant, very, very closely. Very, very closely. If you see, your R has gone high slightly after the clock has gone high. So there is a certain delay. Okay, and then it falls. Then again your clock goes high, right? And that time your R is 1 and your S is 0. So again after a delay, your Q goes low. Okay, so this is the kind of behavior of your SR flip-flop. So there is a certain delay in the SR flip-flop. And SR flip-flop is controlled by your clock. So immediately after your S goes high or R goes high, doesn't mean that your output will change. Okay, doesn't mean your output will change. There's a delay. And delay is also clock dependent. At the time when the clock goes high, when it is positive triggered, that time it should happen. If not, it will not work. Okay, let us dock this now. Mm. Okay. So there is a demo of the SR flip-flop. Now, let us go to file. Let's try the toggle flip-flop. Okay, there's a toggle flip-flop. We'll save it as this point. Toggle flip-flop. Okay, so this is a built-in toggle flip-flop. This is a pulse and this is the clock. Okay, clock. Let us see the output. Okay, this the issue with digital display is not easy to understand. So let me make it dedicated grid. Dedicated grid here. Okay, it looks better than same. Okay, let us see over here. Let us undock it. Undocking really makes it look better. Okay, here. So since it's a flip flop, you need to have a high frequency clock. So you have a high frequency clock coming. Okay, and then this is your T is 1 over here. So when it rises after a delay, it is toggling. Okay, it is toggled. Then again, after the rising edge, after again a delay, it is falling. Then another clock comes and again t is 1, so it toggles. Another clock comes positive edge, again it toggles. After a delay, delay is always there. Now, it is gone low over here, right? Let's see. So over here, again, there's been a positive clock, but your T was high. So that means it toggles. So that means it will rise. But then now your T goes to be 0. So even though you give your pulses after pulse after pulse after pulse you give, it will not flip. Your bit will not flip. Then after some time, again, you have made T high over here. Let's say where over here. Yeah. Okay, your T has gone high and then your clock has gone high. So when that happens, it will go low. And then again, because your T remains high, it will, go low, toggle, it'll keep on toggling. So this is how, like your T is basically like an enable. If your T is high, means your output will keep on toggling, 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 toggling. But if your T is made low, your output will retain its original state. Okay, and since it is positive edge triggered, and there's always a delay in the flip flops. There's a certain delay is present in the circuit. Okay. Now let us go to simulator. Let us go to advanced options. Maximum time for 300 nanoseconds. Let me make it 1 nanosecond. And then now let me run the simulation. Let us check whether it is because of that time step. Okay. No, the delay is still there. The delay is part of the flip flop. It is inherent in the flip flop. Toggle. Go to place. Digital. Okay, so there is a certain delay in the flip flop, which we'll have to look into how do we adjust the delay. All right. So let us look at one of the questions and try. You have this D flip flop, and let us try to analyze this circuit. Okay, let us go for file view. D flip flop. Oh, it's bit advanced. Okay. Save schematic as over here. D flip flop, save it. And run it. Depending on D, your Q will change. Goes 1 here. Then the next clock comes, it goes low. Then next clock comes, also it remains low. Next clock comes, then it goes high. Okay. Reset is there, just an external reset is available. So let us remove, don't need this. Don't need all of this. Okay. So Let's check how the output looks now. Depending on your D, D is always high. Q is taking that. Okay. So it is not basically resetting it. It is fine. Delete this. What we can do is we can use a connector. These connectors, module port. This will rename it as clock. Okay, clock. Take it here. Invert this. This is basically your code. Okay, fine. Now let us delete this. We have to duplicate this circuit. Here we had one more like this. Okay. We had it further over here. And further over here. Sorry. So 4 D flip-flops were needed. Now what do we have? This is going directly. This is going here, right? R also is going. So this is your. This is what your Q. This is Q. This is going here. This is your R. Okay. Similarly, this is going here. And this is your S. Okay. And then we are having T bar. This is coming over here. Okay. And this is T. Okay. Now we have to have an AND gate. But AND gate to what is our AND gate given by Q bar and T bar? It is T bar and Q bar that is it. This is our output Y. Okay, let us simulate this. So also what was the clock was given for clock is any value. This is the output. Just run it for more time. 5 micro. Let us make it what 25 micro. What is the clock period is 500 nanosecond. 1 micro. 1 micro for single pulse. Okay. Just run it now. Comes like this. Just flip. Make it this much slower. 1 micro. Let us make it 50 micro. Let us make it 25 micro. Okay. Simulator choose analysis. Make it 500 micro. Process off. Let's run it now. Yeah. This is what we had seen. So basically, sorry, you have your clock here, another clock here, clock here, clock here, all these. So you have first, so all initially was zero. So it is 0, 0, 0, 0, everything was reset. Then your first clock comes. Okay. Since all was zero, y was one. First clock comes, q becomes one because it is t bar. Rest all just take the value, previous value, so it becomes 0, 0, 0. And your y also becomes 0. So it goes on like that. And then when is it repeated? After 8 pulses. After 8 clocks, it is repeated. You get your pulse again. So this is how what we did. Like you can see, it is getting delayed, delayed, delayed. Like R is the delayed version of Q, S is the delayed version of R, T is the delayed version of S, and Q is the delayed version of T bar. Okay, if you see, Q is the delayed version of T bar. Okay, that is how it has been connected. So that's how what we did has come out to be correct. Okay. So this, let us save it as, save schematic as um, assignment उसको 7, assignment 7 question. Okay, so this has been verified. We have made a D flip-flop based arrangement we have used, and we have checked that what we got as an answer as well as we have simulated it. So we got the actual feel of how our circuit will work. Okay, so it's a very interesting thing. The Simetrix elements is very powerful, very fast. It is a freeware. You can use it for understanding the sum, get more insight and everything. There are certain things which will take time and practice and effort for you to go become proficient with these spice simulators, everything. But it is richly rewarding. It will help you to believe like what you have taught, what you have analyzed, what circuits you have solved by hand. You believe, okay, I'm doing this, I'm giving this input, I'm getting this output, and you will also get slowly get more exposed to practical problems and difficulties which you will face. Okay, so this is a very simple thing. You could also refer to this and make your own circuits, understand how to make your own circuits and do it. All right. Okay, as we have some time, let us also try this one as well. Let us just simply try it off. So what is it? Question number 10. Assignment question 10. What is there in this? You have a clock is there. Okay. It's slightly different. Let's change it. Delete. We only have three flip-flops, three D flip-flops. So D flip-flops are widely very popular. So only clock is required. Okay. So this is your Q0. What is going as an input? Q0 bar is going as an input. So this goes here. Instead, Q0 bar is going as an input. So Q0 bar is an input for your second flip-flop. Now, the output of the second flip-flop is ANDed with the input of the first flip-flop. Okay. So you need to have an AND gate again. So this, let us shift it further. Okay. So this is what, this is your Q1. Q1. Okay. Now you need to add a place. So it's part AND gate. So AND generic gate. Okay. How many inputs? Two inputs. Okay. AND gate is added. Applied here. Let us make the delay 10. Let it go smaller delay. And then it is going from Q1 bar. So here it is coming from Q1 bar. And the first one is coming from Q0. Okay, it is coming from Q0. So this is coming from here. Okay, so sorry. So it is Q0 and Q1 bar. Next, Q2 bar. Okay, this is so this is your Q2. Q2. And Q2 bar is an input to the first flip flop. So it comes from here, it comes over here. Okay. So we have built the circuit. Let us now simulate and check it. how it looks. Okay, let us undock it, look at it, right? Try to get more space. Got myself out of the frame. So what we had previously seen, also they have told us something. What they had told in the question that it should start from 0, 1, 0. Okay, it should start from 0, 1, 0. How do we make sure that our circuit starts from 0, 1, 0? So this is set 0. This should be, this is what digital ground. Okay, I don't want it to be digital ground. I want to connect it to digital supply, digital VCC. So this is connected to, so I connected to VCC. So it is 0, 1, 0. And now let us simulate it. Close it off, close, simulate. Set 1 and reset is not happening. Issue is there. Okay, let us go to the previous ground only and let us see how it works. Okay, this undock. So it was 0, 0, 0. Okay, let us see in our combination, did we ever have 0, 0, 0? Unfortunately, we did not have 0, 0. Because if it was 0, 0, 0, then it would have continued in a progression, same level this, but it is not. To check why it is not working with set, reset. Set is 1, reset is 0. Now in this case, the output is starting from 0, 0, 0. Reset is 0. Okay, let us make reset to be high. Okay. Place digital, this digital VCC. VCC, copy it, paste it here, connect it, okay, connect it, connect. Let us check now what is the initial condition. Okay, everything is 0 in this case. If reset is high, then everything is 0. Okay, so that means we cannot have VCC. So it should be, let us do Control Z. So it is all being connected to ground. It is connected to ground. It is connected to ground, everything is starting from 0, 0. Okay. Suppose set to I replace with digital VCC. Digital VCC. Connect it here. Check now. No, it's not working. Something is not correct. Place digital pull up initial condition. Okay. Okay, I'll have to check regarding how do I set the initial condition for D flip-flop. But I'll look into it, and hopefully next class and all we can look into something similar and certain similar things. Okay, but just I like to really encourage you guys to check simplest elements. It can do various things. I'm also learning it. You also can learn it. You can check your circuits. You can understand it. It will help you when you go for the projects, when you go for interviews, when you have seen how the output should look like, when you get an understanding and that knowledge. And the advantage with simulating circuits is you get the timing diagram, and also you can add certain delays and you can see the actual timing diagram. When you change the delays, you can do your worst case analysis, you can do Monte Carlo analysis, you can do various other aspects. Okay, all these will strengthen the concept more and more. Okay, it will take time. I know it will take time, but I feel it will be quite rewarding for you guys if you learn this circuit. Check, is this connected? Yes, it is connected. Okay. Okay, so we have done various things. we have solved a whole lot of questions, and we have done it in a very fast speed. We have understood that JK flip flop is a very important thing. The characteristic equation of the JK flip flop is very useful for you guys. And also we have done simplest. We have done element simulation. Okay. Okay, so thank you. So we will see for the next session with week 8, we will look into it and we will learn it and we will try to solve certain sums. Okay, so thank you.